nonlinear permanent magnet. In this example, we have two permanent magnets glued to the steel core, and there is a movable steel yoke. Both the permanent magnets and the steel features nonlinear properties. That is, instead of constant magnetic permeability, you have to specify the BH curve data. My task is to find the force acting on the yoke as a function of the distance between the permanent magnets and the yoke. I'm going to simulate a plane parallel DC magnetics problem, ignoring the third dimension. To automate force versus distance calculation, I'm going to use the label mover tool. Okay, let's start QuickField now. In QuickField, I create new problem. Magnet. Next. Problem type is magnetostatics. Model class is plane parallel. Length units are centimeters. Finish. On the left, you can see the problem pane, and on the right is the geometry model editor window. First, I insert a rectangle with the dimensions 40 by 10. Insert. This is the core. Then I insert a rectangle with the dimensions 10 by 10 centimeters, located 20 centimeters to the left and 5 centimeters up. Insert. This is left permanent magnet, and this would be the right permanent magnet. And I'm going to insert a rectangle with the dimensions 40 centimeters by 20 centimeters, located 20 centimeters to the left and 25 centimeters up. Insert. Close. This would be the yoke. In fact, the magnetic field is distributed not only in these parts, but also in the air outside. So I'm going to draw the air block boundary. Switch to Insert Objects mode. Change the line type to be the half arc. Zoom out and draw the air block boundary. Now let's assign labels. Through labels you can explain the geometric object's meaning and provide material properties. Switch to Select Objects mode, click to select and type in the label name. This would be the air. This would be the yoke. This would be a core. This would be the magnet magnetized up. Permanent magnet up. And this would be the permanent magnet magnetized down. Okay. And I'm going to assign the label to the external boundary. Hold the Ctrl button pressed to select multiple objects. External. Now let's provide physical properties for these labels. Double-click the label name in the tree. Magnetic permeability of the air is 1. Okay. For the core, I should specify the BH curve data. I already have the data prepared. Here you can see the dependency. I simply select and copy this data and paste it here. Close. Okay. The same material is used to make yoke, so for the yoke I specify the same BH curve data. Close. Okay. For the permanent magnet, first I should specify the magnitude of the coercive force. It is 147 kiloamperes per meter, and the direction is up 90 degrees. Then I set a nonlinear flag, and here I should type in the BH curve data. I already have the data prepared. Here it is. This is the BH curve for the permanent magnet. So again, I Simply copy this data and paste it here. Close. Okay. Second pigment magnet is made of the same material with the same coercive force, but now the force is directed down, so this is minus 90 degrees. And I will use the same data of the pH curve. Okay. Far away from the pigment magnets, the magnetic field fades to zero. So at the external boundary I specify zero magnetic potential. The geometry model and the data are ready. Before I could start the analysis, I should build the finite element mesh. Now save all problem files and solve the problem. Let's take a look at the results. You can see the magnetic field lines. Let's zoom in. The magnetic field lines looks broken. That's because of the insufficient mesh quality. Let's solve and refine to get more accurate results. Okay. You see the mesh was automatically adjusted. The problem was simulated. Now let's take a look at the results. Let's again zoom in. Now the field lines are smooth curves, as it should be, and the field picture looks physically correct. You can adjust the field picture and switch on, for example, the color map of the flux density and the vectors of the flux density. And the correspondence between the colors and the numbers you can see in the legend. My task is to measure the force acting on the yolk. To be able to do so, I'm going to use the contour tool. Click to select the block, follow to the integrals, and this is the mechanical force. The problem is symmetrical, so we should only have the vertical component of the force. The x component is just a calculation error, and the error is really small, it is less than 1%. Now this force is calculated for this position of the yoke. To calculate the force for other position, I should change the geometry model. Open the geometry model, select the yoke, right click, move selection, displacement 0.5 centimeters down. Okay. Rebuild the finite element mesh, solve the problem. Open the results, use the contour tool, click to select the yoke, integrals, mechanical force. It was 1267, now it is 1397. I can repeat the steps and calculate the force for different yokes position, but there is a way to automate the repetitive tasks. I'm going to use the label mover tool. Label mover can move labeled objects and calculate integrals for labeled objects. To be able to calculate the distance between the yoke and the pigment magnets, I am going to add an edge to the model and assign it a label distance. Switch to insert mode, line type straight line, add the edge, switch to select objects mode, click to select distance. The question mark here means that this is a new label, it is undefined. In fact, there is no physical properties that I should assign here, so I simply click OK, and now you see the zero mark. This label is no longer an undefined, it is an empty label that doesn't hold any physical data, and it is simply ignored during the analysis. Okay, now save all problem files and return to label mover. In label mover, I should specify the base problem. It is already selected. Next, I should specify the values to measure. Add values. I'm going to measure the length of the distance edge and I'm going to measure the force acting on the yoke. Close. Next, I should specify what should be changed. Steps, record steps. I'm going to move yoke by 2 centimeters down. Add step. Close, and I'm going to repeat this step while possible till the yoke hits the payment magnets. Okay, I have the base problem defined, I have specified values to measure, and I have specified the steps to perform. Everything is ready to get the results. You see, a set of problems is generated. In each problem, the yoke is moved to a new position. After all the problems are generated, they will be solved, and the force acting on the yoke and the distance between the yoke and payment magnets will be measured and stored in the table. On a multi-core processor, label mover may start solving several problems simultaneously. Now everything is ready and you can see the results. Distance length and the mechanical force. The force is pointing down, so the y component is negative. When the yoke is far away from the payment magnets, the force is small, and when you move the yoke closer to the payment magnets, the force magnitude increases. If you search for the nonlinear payment magnet on our website, you will find the example page. Here you can read about problem setup, browse the solution section, take a look at the result pictures, and download the simulation files. Simulation files may be opened and the results may be viewed using any QuickField edition, including QuickField Student Edition, that you can download from our website for free.